All right, so yet another location for recording video. So what we're going to be doing today, or in this segment, I should say, because it is a different day actually, is talking about how you use graphs to analyze data. And so this topic really falls under one that is called graphical analysis of data. So here's the thing in graphical analysis of data. We're going to take one set of data, okay? So this is for any set. So this is like singular, right? Any set of data. So take one set. And we're going to graph it three different ways. So we'll either graph it as zero order, and I'll explain this in a little bit, but we're going to graph it as zero order data and see if it fits the model, okay? So, and then we're going to graph it as first order data and then see if it fits the model. And then third order data and see if it fits the model. Now, all three of them can be graphed, so that's not the thing that tells us what the order is. It's which one looks right. And so how do I explain that? So the way our models are designed is for the data to be a straight line. If the data doesn't come out as a straight line when it's graphed, then it's not that model, okay? So in our heads, we have a model of how a cat, a chicken, and a bird, a chicken and a dog look. Let's say cat, chicken, dog, right? And if I show you an animal, what your brain does is tries to fit a model to one of those images. And then somewhere in your brain, it has, even though not all the cats, all the chickens, they don't all look the same. But when I show you one, you kind of know, oh yeah, that's a cat, a chicken, a dog, right? And that's what we're doing. We're trying to develop this sense of when it looks right. And so we're going to show you data graphed three different ways. The one that looks right is probably the best model. Now, there's ways to determine this mathematically. It's called a regression. We won't spend a lot of time talking about regression because that's a statistical topic that's usually it's like a 50-50 chance that you've gotten it, but it'll give you an idea of like when you know it's a good fit, okay? And it's pretty simple, actually. I think it's pretty simple. Let me say it this way: it's pretty simple to interpret, okay? Sometimes it's very hard to distinguish between two close models, right? But statistics gives us a way to do that. Okay, so again, like I said, you're going to take one set. You're going to manipulate the data. And this is what I mean by that. You're going to transform it to fit one of these models. You're going to graph it. And then you're going to choose the model that fits the best. And the best model tells us the order. Okay. So again, this is all based on one set of data. This is not the simplest way to do it, but it probably gives you the best, most reliable result. Okay, so let's leave it like that. What we're doing here could also be done using sort of like rate law information, like how fast is the rate changing with concentration, right? We can do that kind of stuff as well. And that's stuff that you've already learned how to do, but this is how we can treat a whole set of data at one time. Okay, so, sorry, I have these noises, and you're going to hear them now. They're usually silent. I have these noises that play in the background, and it kind of keeps me alert. Okay, so anyways, that was one of them. So graphical analysis, and this is actually going to be a first order data, so I'm telling you that up front. But we're going to linearize data, right, by using the equations. Now, here's the thing. The equations have already been given to you. So these are the forms of the equation. This is for zero order, zeroth order, first order, and second order data. When I say linearize, what we're going to do is we're going to graph this is y, this is y, and this is y, and this as the intercept, right? This is the intercept, and this is my intercept. So in order to graph zero order data as a linear model, if it's really zero order data, all you have to do is graph the data. There's no real transformations. The slope will give us the rate constant, okay? So this is why I say the slope gives k. It's not exactly k, because in that case the slope is minus k, right? And then the intercept, which apparently I couldn't quite get on the screen, is related to a0. So in the case of like zero order data, intercept is a0. But in terms of first order data, right, that the y value that we're going to graph is this. So we have to calculate those values, the logs of the concentrations. The intercept will relate to the log of the initial concentration. And your slope, though, will still be minus kt in this case. So again, that will give us the rate constant. Now, remember, this is just one set of data. We're going to graph it three ways, and we're going to see which way it fits the best, okay? And hopefully you'll be able to, well, you can't tell me because it's a recording, but tell me, in a sense, that, oh yeah, that one looks like it's the best straight line, and that's how we tell, okay? If we graph it as second order data, right, we're going to take 1 over concentration, right? The intercept is going to relate to 1 over a0. Now, these are the y values. What we're graphing as x in all of these is time. So one set of data graphed three different ways. And trust me, when you do this like often, you'll use a spreadsheet and it just pops right out. It's real easy. Okay. All right. Ooh, I don't know how that happened. Let's do this. Okay. Okay, so this is a zero order graph. This is actually data we looked at the beginning of this chapter. And you look at that and say, oh, that's a curved line, right? So since it doesn't fit a straight line, right, it's not zero order, right? Now, how do you tell? Like, sometimes it's hard to tell, like, does it really fit a straight line? In those instances, what you should do is actually take a ruler and draw it from the first point to the last point, okay? And then see whether or not the data falls on that line. So I drew a line on the data, and you can see clearly all the data sort of reliably falls below the line, and it will sometimes fall below, it'll sometimes fall above. If it falls above and below the line, it's probably just like noise in your data, like error in your measurements or errors in your instrumentation where you're not actually measuring a very steady value, right? You're trying to guess a little bit. So let's go ahead and look at the next graph. So this is a 0th order graph of this data. And remember, when we did this, use this data, if you go back and you find this data, this will actually be 1 millimolarity unit. When you find this data earlier in your notes, we have already determined that it's first order. I just thought I'd use the same set of data so you could do some comparisons. All right, let's look at the next one. This lets me. I think I've locked up my computer. How do I do this? Ah, there we go. Got it. So this is, notice what we've done here. This is the log of the concentration. Now, typically I do this as a natural log because I just find it easier to deal with natural logs. So I took the concentration, so you can see the concentration here, and I just entered that into my calculator, and I hit the ln button. Okay, and so that's the natural log of that number. Now, your calculator, you might actually have to hit natural log and then put the number in and then hit equals, right? But it's basically the same idea. So let me draw the line on here, and then you tell me in your head and in your room or wherever you're at whether or not this looks like it. Okay, so there we go. How's that look, right? All the points are either above or below or on the line. And so this clearly fits the data. Now we'll come back, because I said, you can use this to calculate, for example, the rate constant. And so we'll do that in a second. And then we'll do it from both the graph, and then I'll use linear regression to show you, okay? So we'll come back to that. Let's look at it, though. So we're kind of not done. This is a first order graph. right? So I graphed the logs of the concentration. These are these numbers here, right? And versus time down here. And it certainly makes it look like a straight line. So now what I'm going to do is I'm going to look at second order data, right? Now, second order, what you have to do is you have to take this original concentration here, okay, and convert it into 1 over concentration. So literally, that first point is 1/1000th. So that first point, that is this first point here, is 1/1000. So this ends up being 1,000 because I took the inverse of it. In the graph, that's the first data point. That's 1,000 right there, right? So it's not important that the scale, what the scales are, but to get the idea, that's how you're, all I'm doing is I'm just taking a number and taking the inverse. And again, I'm going to graph that versus time as my x-axis value, okay? So let me draw the line on it. I think you can see it, and I'll explain to you how my professor, my PhD professor, showed me how to do it. Again, reliably, right? That looks like all the data falls below the straight line. None of it falls in the line. It's not randomly above and below. So this second order does not fit. Okay, so this is second order graph. It's not second order data, but we're taking the data and going through each of the orders to show, like, is it zero order, first order, or second order? And now we can pretty reliably go back and say, yeah, it looks like it's first order, right? So now, if you remember the equation, and I'll go back to it for just a second, for a first order linearized, that's the phrase, data set, right? This is the equation. The slope is the rate constant. So I graphed, right, t is my time, x on the x-axis, and natural log A is my y values. That's why I graph along the y-axis, right? All I need to do is calculate the slope to get the rate constant from the data. So to get the rate constant, I'm going to go like this. There's a couple of ways to do it. You could go like that if you want to, right? But you can also just take it from any two data points. Now let me explain to you the danger of just using two data points. If you use two data points, and let's say there's a small error at 20 seconds, and it's like this, okay? It, in principle, right, that looks like it falls pretty good on a line. If you extrapolate that between 10 seconds and 20 seconds, oops, that's not quite it. It would look something like that. It creates a huge error in your data if the point you choose is, one, got a little bit of error in it, and two, it's close to the other data point. So practically speaking, when I'm talking to students about like doing, sorry, I didn't mean to do that. Oh well, it's gone now. When I talk to students about doing that particular operation, what I tell people to do is say, okay, look at your data points, right? Look for two data points that look like they're pretty close on the line, and then choose them from opposite ends of your data set. That'll cause less error. So for example, let's say this, I'm choosing this data point here, and let's say there's a little data point error here. All that error is then distributed throughout the line, right? It's not like it's a huge error, but it's a small error relative to a small error here, because that x-axis variable, I don't know how to explain it, but it causes you to have more error as you draw the line. So what I'm going to do is I'll use 10-second data at 10 seconds, and then I'll use the data at 60 seconds. Now, if the 60-second data had been like way off of the line, then I would not have chosen it. I would just say, well, that one I will discount, and I'll use one that's next to it, or as long as it's far away from the first one. Okay, so this is like practical like analysis of graphs, right? And then I'll show you how to do linear regression, and you'll never do what I just told you, but that's fine. Okay, so So I'm going to use this data point and this data point because they look like they follow the trend well, right? And they follow the best fit line is what we call that straight line. Okay, so so to calculate the slope, right, it's going to be minus, this is m, is equal to minus 8.74 minus 7.21 divided by, right, 60, I'll write it out, seconds, minus 10 seconds. And so I'll pull up my calculator for this. Oh, actually, I got to unhide my calculator. My calculator's hiding in the background. Let me find it here. There it is. And then let me calculate that value. So it's going to be 8.74, change sign, minus 7.21, change sign. Make sure I got the numbers right. Yeah. And that's going to be 1.5, negative 1.53, and this will be 50 at the bottom, so divided by 50. So this is negative 1.53 divided by 50 seconds, and that comes out to negative 0.0306. Okay, so now the question is, oh, and what are the units, right? The units are 1 over seconds. And when you're dealing with log data, we don't usually think about the units, but this is actually, when I'm doing the subtraction, it's the log of molarity minus the log of molarity, right? So it's this. It's negative, or let me just do this. It's ln of the unit molarity. I'm just doing the units now, minus the ln of the units of molarity. And what does that come out to, right? It becomes ln molarity divided by molarity. And those molarities will cancel out. So there are actually no units on the y-axis when you're dealing with the log. I know it's kind of a weird thing to think about without the numbers, but with the numbers, this comes out to be the log of 1, but there's actually numbers in there, so it doesn't come out to be just the log of 1. But with the units, you can see how they cancel out. So even though a lot of times people just say, well, we don't think about the units or ignore the units or whatever, they actually do cancel out in the calculation. Okay, so that's my rate constant, or almost, right? Because my rate constant should be negative. My rate constant should be positive. So what I have to do then is I have to think about what the equation is telling me. And so for that, I need to go back and look at my equation. And you'll notice that this says that x is t. That means your slope is negative k. So since my slope is negative k, right, m is equal to negative k, that's equal to negative 0.03061 over seconds, or seconds to the minus 1. I know I'm kind of inconsistent about the way I do it. I just don't really think about it that hard, and I should, for teaching's sake. Anyways, that just means k is equal to 0.0306. And see, I'm going to just do this, seconds to the minus 1, because it's easier to write and I'm running out of space. All right? Okay, so this is how we use graphs to determine orders of reactants, and also how we use graphs to determine a rate constant. Now, I said the little bonus feature here, let me end the slideshow, and I'll show you how to do this in Excel. So I don't usually show you this part. The handwriting's all still there, right? This is actually an embedded Excel graph. And so what I get to do with an embedded Excel graph is actually use Excel functions. So I'm going to click on this data point here. I'm going to right-click on it, and I'm going to add a trend line. This is what it's called. And there you go. There's your straight line through the data. You can see it. It sort of just did it all by itself. And then I want to display the equation on the chart. So that's that. Oh, look at that. It's usually like 0-point font and you can't see it. And so there's the equation on the chart, right? And notice what it is. It's negative 0.0304x minus 6.9078. That's the y-intercept, right? Now, the actual zero time value was 6.91, so it's actually pretty close, right? Negative 6.91. And then the slope that I calculated was negative 0.0306, and this comes up with negative 0.0304. Now, which of those two values is better, right? Well, it turns out they're both pretty good. Like, it's not significantly really that different. In terms of sig figs, we only have 2 sig figs in our data, and so that's probably all the best we can expect anyway. So they're actually very close within significant figures. Now, here's the other thing. I said I would tell you how we can figure out what the best fit is for the data to align. And in order to do that, I'm going to right-click on my data set again, right? And I'm going to go like this. I'm going to add a trend line again. And it already remembers that I added some stuff. But I'm going to display the r squared value. Now, r squared, right, varies in its value. It has a range of values. And it's really from plus 1 to 0. Now, there's a thing called an R value, and that actually has a range of values from plus 1 to minus 1, but we square it sometimes just to make the analysis easier. The closer that value is to 1, right? The closer the value R squared is to 1, the better it fits a straight line model. So this data fits extremely well. The sort of the standard in analytical chemistry when we try to create straight lines is from our experimental results. The standard is try to get 3 or 4 nines in the correlation coefficient. If R was 0, that means the data is completely uncorrelated. And statistically, there's ways to sort of measure like how well it fits, but we don't need to know that kind of thing. Like, does it fit 99% confidence limit, 95%? There's ways to do stuff like that, but we're not going to worry about that. If you're only using R, and your calculators will give you R, and you could just square it. But if your calculator gives you R, it's the value. It's the R needs to be closest to 1 or minus 1. So if I had looked at R for this particular experiment, it would have been minus 1 because the sign actually just indicates the slope sign. So if the trend is going up, it's positive. If the trend is going down, it's negative. Okay. All right, so that's how you would use, again, Excel if you were to do it. This is actually an Excel spreadsheet embedded into my PowerPoint, so I can go back through and change data points if I want to. And I would regraph it. But really, that's how people do this. They'll take an Excel spreadsheet, they'll put their data into it, they'll use equations to convert all the values over, and it only takes about 2 or 3 minutes to generate all these graphs. The hardest part is just getting like a white background and black lines, because PowerPoint and Microsoft don't feel like you should just have black and white. They always have these billions of weird colors. Anyways, that's a little bit of a complaint. Sorry. I spent an hour just formatting 3 graphs. It took me 5 minutes to make them all. All right, I'll stop. Okay, so here's a quick summary on graphing data, right? When you have data and you can't immediately tell it's first or second order. Like, say, for example, there's not a lot of data collected, or you can't see enough information to look at half-lives, things like that. Then what you do is you create a graph, right? And you make 3 graphs. You do a 0-order plot, first-order plot, and a second-order plot. Whichever one is straighter is probably correct. And if you really want to get technical about it, you can do all 3, compare the correlation coefficients, and whichever one's closest to 1, right? That's the one that you would choose. Okay, so just going to show you this. This is actually worked out for you. It determined the order and the rate constant, but I actually wanted to show you something in the data that tells me already that this is second order. Okay, so just to show you that. And then the rest of this is worked out on the slides. And so if you like go through the slides and look at this data and try to do it yourself, it's all worked out and you can see it. Okay, so I already know that this is second order data, and this is how I know it. Well, one, I graphed it, but yeah, without graphing it, right? What you're going to do is say, look at this concentration at time 0. Now, half of that concentration is 0.05. That's the half of the concentration there, right? That's 20 seconds. So automatically, I know the first half-life is 20 seconds. I know for a zero-order reaction, the second half-life would be 10 seconds because it's half of that value. I know for a first-order reaction, that half-life is still going to be 20 seconds. So the next half-life should come at 40 seconds, 20 seconds more. Right? The second half-life for zero order should have come at 50. Should have come at 10 plus 20, which is 30 seconds. If it's a second order reaction, then what happens, right? Second order reactions are twice as long as the first half-life. So it's 20 seconds plus, right, 40 gives me 60 seconds. And you'll notice I actually have enough data in here that there's half of 0.050. It's actually 0.025. That comes at 60 seconds. So this is second order data because the half-life doubled, okay? So by half-life, that's how you're going to do that. So if you wanted to know, for example, what's the rate constant, you can immediately take any two data points and use the equation. So for 1 over AT, right? Oh yeah, I gave you the half-life equation. Sorry. You could just use the half. I was going to start with the original equation. Well, actually, let me show you how to do the original equation too. So, sorry. 1 over AT is equal to 1 over A0, right? Plus KT. So that's the equation for second order data, right? So then what you would do is pick any two data points. So let's say I chose this one and this one. And I'll tell you why I'm doing that in a second, okay? What you're going to do is you're going to put in for AT, you're going to put in 1 over and then 0.033 molar. I don't know what happened to my 0 there, it disappeared. And that's going to be equal to 1 over A0, which is going to be 0.080. So the reason I'm doing this, right, is because you don't have to use the first data point in your calculation, especially if it's bad. If you're looking at a graph of it and it's a weird point, don't use it. Plus K and T, and here's the thing, this is, again, since I'm not using the first data point, it's the time difference between whichever data point I'm at and whichever point I started at. So it's actually 35 seconds, like that. Okay, and then you solve it for K, and then you'll have the rate constant. Now, if you use the half-life equation, then you would do this. So remember, T1 half, wait, actually K, because I want K. K is equal to 1 over A0 times T1 half. Okay, so you would take this value as A0, so K would be equal to 1 over and then 0.100 molarity units, and T1 half would be 20 seconds like this, right? And then what you'll get is 20 times 0.12, so K is 0.5. And the units would be molarity per second. Sorry, per molarity per second, because both are in the denominator, okay? So that's how you would have done with the half-life. Clearly, I didn't do this one because it's just a lot of math and algebra. You can do that part. But I thought I'd show you how to set both up and then do the calculation. Oh yeah, so there's the answer. All right. Yeah, so the rest of this, you might yell at me, is graphing it. Oh, I didn't. Okay, so I already determined that it's second order, but let's say I didn't know, like, I didn't have enough data to get a good idea of what, I didn't get to the first half-life, say, for example, but well, that's kind of weird. You would know that. Anyways, let's just say you want to graph it. Then you would just go ahead and do this technique. And that's worked out, and the graph is shown later in the slides. But I'm not going to show it in the video. You could just do it and then see how yours compares to mine. Okay, so, and hopefully you were able to get it to work, right? This is just a summary of this section because we've already covered a lot of ways to like do the same thing. And this can be confusing. So I just wanted to lay out to you like the different ways, like generally how a rate constant could be determined. So the first way that we learned, and that was early on, it was actually in the first video series, I think, of this chapter. There are concentration-based studies. So what you do is you take the concentration, right, and you change it, right, and you see how the rate of the reaction's changing as you change the concentration. We use that with the general rate law. So for example, for this reaction, you would have said reaction rate is equal to K times A to the X. I'll say A to the A, let's do that, and B to the B. And then what you would have done is you would have said, okay, let's hold B constant, change A, and see what, oh, so I see why I don't do that. I have to keep saying A. All right, let's call that C and D. All right. Let's change A, right, and C, and keep B constant, and look how the rate changes. And then we can determine the order of A, which is C, okay? And then we'll hold A constant, right, change B, all right, and look at what the order is, D, for the reactant B. Right? That's how you would do it. So think about that. That's a minimum of 3 experiments. So it can take some time to do that. But when you do that, then what you can do is you can get the specific rate constant, K, right? Using one set of data that you have for where you have the concentrations. You plug in A, you plug in B, you put the coefficient or the exponents in there, the orders in there, and then you solve for K. Now, if you're going to do an integrated rate law study, right, you use an integrated rate law. You measure the concentration versus time one time, let's say. You usually do it more times, but let's say you do it one time. And then you graph the data to figure out which is the best model. And then the slope, right, is going to tell you what the rate constant is. And believe it or not, there's a lot of other ways to do this. I've read lots of books on this, and there's like as many ways as you can imagine to do anything to do this. Okay? People have their own little pet ways of doing it, but these are kind of the standard ways to do